Hello. So today's topic will be the Laplace equation and an insight into the Fourier series and Laplace transforms. A lot of people have trouble visualizing how Laplace transforms and how Fourier series work. So it's that they can't sort of conceptualize how the geometrical reasoning behind these mathematical objects functions. So today's goal would be to develop an insight using the Laplace equation. It's not that it is tough, it's just not taught to you in a way which is easy to understand, and I'm pretty sure this way would not have been taught to you in class. So let's start. We have something called the Laplace equation. Now this is a partial differential equation, so let's write it down. This is the Laplace equation. So over here it means that time is not defined with respect to time, because I have x and y but no t. So it is with respect to spatial coordinates, and time can be taken as time or whatever you wish, or time, or any other coordinate. But let's think about time, because most of the equations are defined with respect to time. Here time doesn't matter, so this means it's a steady state equation. That means with the passage of time, the way I solve this equation doesn't really change, right? Now we know that this equation, because it's x and y, it will graph out some object in the xy plane. So if I have the xy plane, when I solve this equation, when I get some solutions, they will have some geometrical significance in the xy plane. There might be any shape, or there might be points, but they'll describe something on the xy plane. So for our convenience, let's take something very simple. Let's assume that this figure, when we solve it, describes a circle, right? Because it's very easy to conceptualize stuff with circles. Now whenever you're given problems with the Laplace equation, normally there's something called a boundary condition. So let's say u naught is the boundary condition, and let's say u is a function of x comma y. Okay, so u is a function of x comma y. I've just written as u equals a function of x comma y. Now this means that the values of u depend on the inputs we give it, x and y. So let's try to solve this by just guessing some solutions, because the best way is to first try to come up with an approach and then build a mathematical reasoning as to why those solutions work. So if I were to, let's say, if I were to guess some solutions for this, what would satisfy the dou squared u by dou x squared plus dou squared u by dou y squared equals 0. So one thing I can think of at the top of my head would be all constants, because the derivatives of constants would be 0, and so 0 plus 0 would be 0. So all constants would satisfy. So all constants. So 1, 2, 3, etc. But let's take 1 for an example. Just keep the thing small to understand it. So all constants satisfy it. But we are mathematicians. We don't like these trivial solutions. We want it for all solutions possible. So let's think about some other solutions which might satisfy it. I can think of, okay, x will satisfy it. How? Because if I differentiate x with respect to x, I'll get 1, and if I differentiate again with respect to x, I get 0, and if I differentiate x with respect to y, I get 0. So 0 plus 0 is 0. So x works. Okay. What else will work? The y part of the function will also give the same answer. So I can have x and y also as solutions. What else will work? I think x squared minus y squared will also work. So x squared minus y squared will work. and 2xy will also work. I have a hunch, I'm not sure, but 2xy will work. So how did I get these solutions? Did I just think them? Did I just think about them? Well, it's easy to guess these, a little more complicated to guess these, but you can sort of get them by working in reverse. But higher order solutions, it takes more and more time. So there's a trick which we can just develop to get all solutions, and that trick is all solutions follow the form x plus iy power n. This is just the representation of a complex number. So if I were to, so the n value tells us, what's the degree. So if I have a solution, let's say if the power is 2, so let me square this, x squared plus iy the whole squared plus 2ixy. So the real part will be x squared plus I squared is minus 1, so minus y squared, which I have got, and the imaginary part will be 2ixy. I will come outside the imaginary part, so 2xy. So if we plug in higher and higher powers, we'll get higher and higher order solutions. So this is the formula for solving Laplace equation. Now this seems pretty simple, right? Now, as we were saying, let's say we are coming back to a real problem with the circle which we talked about. So let's say we've been given a problem on temperature. So there is temperature which is a function of x and y, and we've determined the temperature inside the circle. So we've been given the boundary condition. Let's say we know what's the temperature at the boundary. So at the circumference of the circle, we know what's the temperature, but we don't know what's the temperature inside. So we'll try to find it using this formula. So this is in Cartesian coordinates. Whenever I'm working with circles, I prefer to use polar coordinates. Why? It's just simpler, because if you use Cartesian coordinates to define each other in terms like x and y in terms of each other, it's very complicated. You'll get square roots and it just complicates life for no reason. So I would rather switch to polar coordinates. So switching to polar coordinates, you get let's know this as well. So let's take x as r cos theta and y as r sin theta. So the solution was x plus iy power n. So I can write this as r cos theta plus I r sin theta power n. Now r can be taken out as common, so it will be r power n into cos theta plus I sin theta power n. And this, because of the legend Euler, we can never forget what this is. This will be r power n, and you can write this as, this will be e power I theta, so we can write this as e power I n theta. So this will be the solution for the Laplace equation in polar coordinates. So the values from this will give us the temperature or whatever function or whatever function you want to find inside the boundary. So what would be the solutions? Because this doesn't really make sense. So there we talked about the real part and the imaginary part. So here the real part, it's pretty similar. So you have taken r common. So can you guess the real part? Yes. So the real part would be, if you multiply Rn with this, it will be Rn cos n theta. So r power n cos n theta, and the imaginary part would be r power n sin n theta. Right. Now this tells us the solutions, but I don't want solutions for n, I want up till infinity. So how can you say that the solutions are, I want to add all solutions up. So I can say that the final solution, all the solutions are a linear combination of the solution. So you can add some number which will multiply with the solutions to give you the final solution, right? So I can say that it will be, some number, let's say an. Let's take an as the multiplying factor. Okay, so we can take some linear combination. So let's say multiply an, and we have one more multiplying factor bn. So an will, let's say, multiply with r power n cos n theta, and bn will multiply with r power n sin n theta. So if we want to add all of them up, we can say, it is sigma an r power n cos n theta and sigma bn r power n sin n theta. These two should ring a bell. They look pretty sus, they're pretty familiar. What do these look like? These sort of look like Fourier series coefficients. I mean, the terms for the Fourier series. So these solutions together, this would describe all the solutions of Laplace's equation in, some geometry. So this is the basis for Fourier series. This is how we come to Fourier series. How we come to Fourier series. The geometrical basis for Fourier series is this. So I guess that's enough for the first video. In the subsequent videos, we'll talk about the Laplace transform, Fourier series, and for the Fourier transform. Thank you for watching.